Let's go back to the dialogue between the spacemen and the Earthlings. Um, and let's just go in parallel for a minute here. The spacemen say that we are behaving in a situation that's exactly analogous to the travelers. We say the geometry underlying our space that determines what a straight line is must be curved because the straight lines, that is, the path, the tracks of unaccelerated objects in our spacecraft, behave in slightly strange ways. But we claim there's no force at all acting on us, unless you have other forces like electromagnetism. But they're saying there's no real force of gravity. The Earthlings, so that's exemplified by this picture. This is all they detect, and these are very, very small arrows. The Earthlings detect very similar large forces on these objects. For any two objects, there's two similar very large forces, namely the force of gravity pulling down, but only a small difference in the direction and maybe the size, and that's causing this behavior that the spacemen see, that they're all falling around the Earth in a slightly different ways. The spacemen would say, yeah, but that's what our natural thing to do. So the spacemen say the natural state of matter is free fall, just weightlessness and moving in whatever direction you're supposed to go in. And that in interstellar space, that has certain properties. If you're way away from any kind of mass, and near a mass, that has slightly different properties. But the natural state is free fall. According to the Earthlings, the natural state is if there's no gravity, and then there's no acceleration. That's kind of the Newtonian paradise. That only happens away from masses. That can only happen way off in interstellar space where you're away from any kind of mass to attract you. And so the nice advantage, and a very crucial advantage of how the theories work mathematically, is that at this point of view, you can test locally whether you're in the natural state. You can, inside your spaceship with the windows closed, you can just let everything go and see, do things get smashed into the walls? If they don't, we say we're in free fall. And you don't really care that much whether you are in free fall away from a mass or near a mass in interstellar space or orbiting around the Earth. It's not going to have a dramatic effect either way. Basically, you have an apple tree inside your huge spaceship, and you just let the apple go. Does it fall relative to the tree? If it doesn't, then you say, we are in the natural state of free fall. We might be far away from any kind of gravitating object. We might be near one, but it doesn't really matter. There's not a substantial difference. The thing about the natural state according to Earthlings with no gravity, you can't test that. You can't close your windows of your spacecraft and tell. You can't, certainly it's a physical fact that you can't really see a really crucial big difference between being in the closed up spaceship away from Earth and orbiting around the Earth. They're both weightless. And so that's a weird thing, and it's something that that Einstein and people after him focused on as being a weird thing about Newtonian gravity, and this is really superior in a lot of ways. It's local theory. The Earthlings say free fall near the Earth is just really different from motion in empty space. It's going in like a curved orbit around. That's just really, really, really different. And the spacemen say it's not as different as you think. The spacemen say our situation as people watching this video, so you're almost certainly sitting in a chair watching this video. Let's go to the Earthlings first. Their description of the situation is that you have a force of gravity acting on you. There is such a thing. But it cancels with the force of the floor or the chair or whatever's holding you up, and it yields zero acceleration, which is a nice state to be in terms of Newtonian physics. Zero acceleration, but because of a perfect cancellation of the gravity canceling the force of the floor that's holding you up. The spacemen have a very different view on this. They say, you know what? Even though you're just sitting in your chair, you don't seem to be moving. You're constantly accelerating upward. The apples that are on the trees, not the ones that are falling, but the ones that are still attached to the trees, the seat of your pants, they are constantly accelerating upward. That's a weird thing to think about. I'll talk about it more in a second, but think about that. You right now, watching this video, sitting in a chair, are constantly accelerating upward. It's why you feel a push in the seat of your pants. You are feeling this push in the seat of your pants. Whenever you feel a push, if you're in a car and you feel a push in your back, say you're blindfolded in a car and you feel a push in your back, you know that the driver has stepped on the accelerator and you're accelerating. If you feel a push from your seatbelt, you know you're accelerating the opposite way. You're decelerating, putting on the brakes. Well, if you feel a push in the seat of your pants right now, sitting watching this video, you should conclude that you're accelerating upward. And what's going on is that you are constantly turning away from a geodesic. Now, the Earthlings say, that's ridiculous. How can I be turning? I'm not moving, much less turning. Moving seems to be implying going along some trajectory and moving, and then you can see whether the trajectory is straight or not. I think I'm sitting still. And here's a very crucial piece of this puzzle. It's that your path in space-time is curved. You trace out your position both in terms of position and time. And that is what is a curved track. So here's the kind of space-time picture that we draw. This is a schematic one where only one space dimension and one time dimension. But in any situation, and this is not unique to relativity, you can draw this in any kind of situation. And in fact, you draw graphs rather like this in any kind of like a calculus class or something describing motion. You're not talking relativistically. You have space on one axis and time on one axis. And you look at the trajectories in both space and time. So a falling apple has a certain position at any moment, and all those moments in time are recorded here. So this is an event right here in space and time. The apple is at a certain location at a certain time. Here's a person sitting near the apple, and that's all the events on what's called the world line of this person. And notice what I've drawn is I've drawn the falling apple, which the Newtonian description would describe as a curved line, certainly moving and accelerating even. But I've drawn that as a straight line, a geodesic, suggesting that this is kind of the reference standard. You let things fall, and those are going to be the straight lines in space and time. The sitting person, the separation between the falling apple and the sitting person, if you've dropped the apple, the sitting person's separation from the apple is changing as time goes on. Maybe it gets bigger. And what we're going to think of, we want to encourage ourselves to think of the sitting person's trajectory as therefore curved, because we want to think of this as a straight line. And this is what it means to say that you are constantly accelerating away from what you ought to be doing naturally, which is falling, free falling. And that push in the seat of your pants is in fact making you move, making your trajectory in space and time curve, even though it seems like this wouldn't make any sense that you're sitting still. So it's absolutely crucial. This is not a theory about curved space. It's about a theory of put space and time together and describe the curvature of space-time. And so that is a bit of a difference between the parable of the travelers and this situation. But otherwise, there's a lot of similarities. So the spacemen would say, Earthlings, get used to it. You should think of yourselves, it's like you're living on an amusement park ride, constantly being accelerated, or living in an elevator. If you're riding in an elevator and it jerks upward, it accelerates upward very suddenly, you think you get heavier. You think there's an extra force pulling you down, and it feels exactly like gravity. And what this is, the suggestion here is that if you feel a force that's exactly like gravity, like some extra gravity when you're being pulled up in an elevator, well, maybe all of gravity is the same kind of fictional force that isn't really there. That it's basically because you're accelerating away from your natural trajectory that would be free fall. Probably people who do a lot of skydiving probably buy into this theory more psychologically, the idea that free fall is a natural state for people. The truth is we're not used to it. And of course, spacecraft, astronauts actually experience this day after day if they're in the International Space Station. They get used to the feeling of free fall. This idea that gravity is really a fictional force that's exactly equivalent to the kind of fictional forces you get when you're in an accelerating object, like a car or an elevator, is called the equivalence principle. This goes back to Einstein himself, that he said, let's think about gravity as being the same kind of fictional force as you would invent for yourself to explain, wow, why do I feel the push in my back when he push the accelerator on in a car? Why do I feel suddenly heavier when I'm in an elevator, or suddenly lighter when the elevator stops in its journey upward? And it's a cornerstone of general relativity, the equivalence principle. Well, the Earthlings continue and say, now wait a minute. Okay, this seems really weird, but maybe you're sort of slightly trying to convince me here. What about the small discrepancies? What about the fact that you put 5 objects in the International Space Station? They don't all just sit right next to each other and not move. They do move slightly relative to each other. at least the small discrepancy is the evidence of a force. Even if you can convince me that the general motion down or falling around in a circle or whatever gravity seems to be doing from my perspective, even if you can convince me that the big force isn't real, the small discrepancies, even you admit that those are real. Isn't that evidence of a force? Okay, but that's very much like the idea of the force that seemed to be exerted by on the travelers, and we just determined that that was really a geometrical effect. So the spacemen say, well, this is exactly like the situation with the travelers. The effects are negligible locally, and they're only noticeable globally. Here's the situation with the travelers. Suppose they had started 1 meter apart on the equator, say, and they traveled north 1 meter. The difference then in their separation would be utterly negligible. It would be incredibly hard to measure. Even when they went 200 kilometers and their initial separation was a pretty big 10 kilometers, even then it was really hard to measure. It was still only 5 meters closer out of 10 kilometers. It was still a tiny effect. You need to have some sort of fairly large travel in order to get even a tiny effect, much less a big effect. Okay, well, the Earthlings come back and say, well, wait a minute. How do you explain the huge effects that are just present every day in terms of gravity? Why don't you try jumping out of the balloon and see how you like it? You're going to fall 250 meters in 7 seconds, and you're going to die. Isn't that saying gravity is a real force you have to reckon with? And the part of that claim is that 7 seconds is a pretty quick time to go 250 meters. And in particular, that doesn't seem to make sense with this description. To get some sort of really noticeable effect, is 7 seconds really a long enough time? Isn't that kind of analogous to something like this? That doesn't seem like a long time. Maybe if you let something drop for many seconds or many hours or years, I could believe you could get a big global effect out of that. Okay, so let's go back to that picture. You have two objects separated by 25 meters, and you let them drop 7 seconds, and they have this tiny difference in separation after a 250 meter fall. Everybody's agreed on that we definitely need to explain the 1 millimeter closer. But they have radically different opinions about the 250 meter fall and the 7 second fall time. The Newtonians say that's a drastic effect. You're going to die. It's 250 meter fall in a quick amount of time. The people in the Einstein perspective, the spacemen, people I've been calling the spacemen, have a different perspective and say that, well, that's exactly what you should be doing. It's the balloons that are doing something unnatural by hanging up there in the sky. The natural state of motion is to fall. I don't feel there's a need to explain the fall so much. Okay, so the spacemen would also say, you know, the thing about these small effects that we see, especially with the travelers, they keep adding up, and they can add up in interesting ways. With the travelers, remember, they started out the 10 kilometers apart, and then when they travel 10,000 kilometers, well, 10,000 kilometers is exactly enough to get them up to the North Pole. That's where a drastic effect happened, where they couldn't ignore, even if they didn't have good measuring devices, the fact that they were on a curve in a curved geometry, that these things all converge together. And 10,000 meters happens to be 10,000 kilometers rather, happens to be almost exactly the distance from the equator to the pole. That's why a meter is defined the way it is. Okay, so the spacemen say, let's try to figure out how maybe a huge effect and the idea and the fact that gravity pulls things to the Earth can actually be thought of in a very interesting way as adding up a bunch of small effects. And here's the way you do that. This is really cool. What you imagine is you imagine a ring of balloons all around the Earth. And I'm going to drastically exaggerate how far they can get away from the Earth here, okay? But just for the purpose of the picture, okay? They're still starting out just 250 meters above the Earth and then dropping all their chilies down to the surface of the Earth. And I'm going to have a ring of balloons all the way around the Earth, and they're all starting out at the same 25 meter separation. So there's going to be a heck of a lot of balloons. And then they all drop their chilies, and the chilies land in the corresponding positions down here. And the 25 meter separation between any consecutive pair of chilies has now been reduced to a 24.999 meter separation. That's that small effect that you expect from this kind of thing that the travelers experienced, that you don't expect huge effects from the curvature of space and time, but you do expect these small effects. But here's what happens when you consider them all together. The circumference of this this circle has decreased because it's a certain number of balloons that were all 25-meter separation. The circle of the Chiles has exactly the same number of Chiles, but they're all 24.999 meters apart. So the circumference has decreased by 1 part in 25,000, 1 millimeter out of 25 meters. So that must mean that this circle has to get smaller. The radius also has to decrease by 1 over 25,000. So this is a very weird explanation. It's going to seem exactly backwards. It's going to say that the Newtonians say the reason that they ended up closer together is because gravity's pulling them into the center of the Earth, and of course, therefore the radius decreases, the circumference decreases, and they have to fit into a slightly smaller circle. The general relativity description is exactly backwards from that. It's saying that they're not really wanting to necessarily go anywhere, but there is this small effect, this kind of tidal effect, that says that as the two Chiles both travel on their natural straight lines in space-time, they're going to get slightly closer together because of the geometry of space-time. And that measure is just 1 in 25,000. But the only way for them to do that is to slide in to a smaller circle. And guess what? If the radius decreased by 1 over 25,000, or the circumference decreases by 1 over 25,000, well, the circumference of the whole, the radius, was about 6,400 kilometers. That's the radius of the Earth. 6.4 million meters. Divide that by 25,000, you get 250 meters. And so this is a really cool way to think about gravity, is that the Chiles really kind of want to get ever so slightly closer to each other. And the only way to do that is for them to fall 250 meters. And so that's saying that yes, there is a big overall effect in a way, that these Chiles all have to fall to make things consistent, but it's not that the 250-meter fall caused the slight decrease in the separation. It's more that the slight decrease in the separation is the real crucial thing. And you add that up, the only way for that to be consistent with all these things in a ring is that the ring must be getting smaller by 250 meters. Also, now there's this other objection by the Newtonian folks, the Earth, what people have been calling the Earthlings. Wait a minute, this all happened in 7 seconds. That's quick. And of course, part of the significance of it being quick is that's why you die, is that you end up with a high velocity. And so the Einsteinian point of view, the spaceman's point of view, has got to answer that. Well, remember, this is all about motion in space and time. It's about one of these kinds of diagrams, moving in space and time. And when you put together space and time, you've got to have consistent units for that. And this is the one place where we really have to bring in special relativity a tiny bit. And all we have to bring in is the fact that the right way to have the same units for space and time is relate them with the speed of light. And so 7 seconds, it turns out that light travels 2 billion meters in 7 seconds. That is, in fact, not a short distance. It's a very large distance. So the 7 seconds, if you convert it to the units of distance that we're using for the rest of the problem, meters, kilometers, all that stuff, it actually turns out to be a huge distance. So in addition to traveling 250 meters down towards the Earth, they're essentially also traveling billions of meters in time at the same time. And so that's enough to give a fairly decently large effect. Okay, so the speed of light is hiding in here. And so in fact, there's a large distance essentially covered in the time direction. And so that's not that surprising that we could get dramatic effects by both of these processes. One is realizing that the 7 seconds was a large amount of distance when we convert it in the speed of light. And the other is that these tiny little effects, if you add them up over all these hypothetical balloons, they can create a very large effect to make it all consistent and make the geometry work out. So this is interesting. Riemann, famous mathematician, famous for the Riemann hypothesis, he actually made some attempts to come up with a geometric theory of gravity, but one of the reasons he couldn't do that, even though he invented a lot of the geometry that is used in general relativity, is he didn't realize it had to be a space-time theory. And he could see examples where the curvature of different objects, like the curvature of the track of a bullet, is very different in space from the curvature of like a baseball tossed up in the air. And he couldn't reconcile that because he didn't realize that it had to be a space-time theory and that the speed of light would be crucial for that.